Okay, so far we've gone from first order ODEs to second order ODEs, and then we've looked at linear constant coefficient second order ODEs. We said a few things about variable coefficient second order ODEs, and then we very quickly jumped into the qualitative stuff, phase space analysis and so on. And I said a few things about how the general 2D first order system, which is equivalent or to which any second order system can be brought into, how it behaves in phase space. We classified fixed points, and then we saw how to determine the stability of these fixed points and so on. And then finally, we said that this entire idea can be extended to nonlinear second order ODEs. And that sort of wraps up all we can say about nonlinear systems without actually solving them explicitly. And by solving them, I mean by numerical schemes. And I will discuss numerical schemes, I think, the next session, which will be the last one on differential equations. Now, let me start today by looking at the hierarchy that we started all the way maybe 5-6 classes ago, which was that in any situation, the best bet we have is this exact or closed form solution. And then we said the next best thing was a series solution. Or quadrature, of course, which means you write y of t is some integral of some function, and then you don't have to solve a differential equation, you just have to evaluate an integral numerically, and then you will get the solution. That is the next best thing, of course. And then we said qualitative methods. And then finally numerical solution. Right, so far we've discussed this, of course, that is for the constant coefficient case we've done that. And we also discussed this, first order and second order, what do you do in phase space, you know, how things change and so on. And also we've talked about bifurcations and qualitative changes in the nature of solutions and so on. So now what we'll do is we'll look at this. Okay, today we'll look at this, and in the next session we will look at this. And the reason I'm only spending one session each on these is not because there is nothing to say, of course, but because there is too much to say. So you could have a complete class, full course on just series solutions, looking at regular points, singular points, perturbation, asymptotics and things like that. And of course, you can have an entire course on numerical methods itself. So for initial value problems, boundary value problems, convergence, rates of convergence, things like that. So the treatment that we're going to have in the next, today and the next session, is necessarily as a result going to be fairly introductory. I don't expect too many people to have seen these ideas fully. Of course, you must have seen it in some form or the other, but what we'll do is I will give you an overview of series solutions, where they come from, where they fit in the big scheme of things, and where they can be exploited. And this, again, what we will do is only series solutions for linear equations, but any variable coefficient. Okay, it doesn't have to be constant coefficients. That's the whole point of it. Constant coefficients we know how to solve. So any arbitrary linear second order ODE, you can apply series solutions and you will get some result, some result that you can use. Okay, so that's what we will see today. And the numerical schemes, of course, you can use for any nonlinear system. And if all this fails, of course, this will fail, this will fail. This also, if it fails and you want an exact trajectory, then this is the only recourse you have. Okay, so I will talk about initial value problems in the context of numerical schemes, pardon me. And I will also mention maybe what will change if you have a boundary value problem and why it becomes a little bit more complicated. Okay, so let's start with this series solutions. Now, the idea of a series solution, I'm sure, is not new because it's intricately tied into several ideas that you already know. Okay, so let me start right at the beginning where I talk about. Okay, let's step back a little bit. Let's step back, and then we've been so far discussing only IVPs, right? Initial value problems, second order ODE. You give y at t equals 0 and dy by dt at t equals 0 or t equals t naught, whatever, some point at which both y and dy by dt are specified, and then you just solve the equation after that. That was the basis for all the phase space stuff that we discussed. Remember, if you had a 2D differential equation, you have y1, y2, and then in an initial value problem, you specify the coordinates of the starting point, because you specify if this is, let's say, p and this is, let's say, q, some constants p and q, then at t equals 0, the trajectory starts here, or the solution curve starts here. Okay, this point. So what does this mean? This means when you specify y1 at t equals 0 and y2 at t equals 0, of course, and then if you have a second order system and you cast it into this equivalent 2D first order system, then that is basically y, and that is dy by dt. So you give y and dy by dt at the same point and trajectory starts, right? You've seen this. Now the problem with BVPs or boundary value problems, the complication is as follows. If I specify y at t1 and y at t2, that's a typical boundary value problem, right? It's a Dirichlet boundary value problem. I could also alternatively specify dy by dt at t1 and dy by dt at t2, or some combination of the two, right? Y at t1, dy by dt at t2, and so on. We've already seen that. If I specify this, then what I'm actually looking for in phase space is a little bit more complicated. Here I know what this looks like, so at this point I can start my trajectory and start looking at the local dy by dt, dy by 1 by dt, dy by 2 by dt, and then actually start solving it over here. That's possible. Especially you will see that this is possible when you do numerics. But here what I'm actually specifying is the following. So if I specify y at t1, y at t2, remember y is the coordinate y1, dy by dt is the coordinate y2. That means I'm saying if this is, let's say, p and this is q, then I'm saying that at t equals 0, the trajectory will start somewhere on this vertical line, because all the points on the vertical line will have the same value of y1, that is equal to p. Okay, so at t equals 0, trajectory starts from somewhere on this line. Okay, we don't know where, it starts somewhere, because we haven't specified the slope, so we haven't specified y2. Okay, but we know that at t equals not 0, t equals t1, sorry. Then, but we know that at t equals t2, it must end on this line. Okay, trajectory must end on this line at t equals t2. So that gives us a condition that no matter where I start, I must end on this line. And using that, I'll have to back calculate the trajectory. So presumably I'll start at different points here, see where the trajectory goes. Only some of them will end up at this line at t equals t2. Maybe all of them will eventually cross this line at different t's, but I want it exactly at t equals t2. So only some of them at t equals t2 will cut this line. Let's say this trajectory which I started here cuts this line at t equals t2, then this is the actual trajectory. Okay, so boundary value problems are a little bit more complicated. That's why we've sort of sidestepped them completely so far. So now it's I think about time to come and readdress this issue. In order to do that, we'll step back a little bit and see where do IVPs and BVPs come from. Where do they come from? And we'll give some type of physical background for this, starting from PDEs, so that you appreciate their roles and their properties. So the boundary value problem has some unique properties. I think once we discuss this, that idea will come out. Okay, they can be thought of as eigenvalue problems in some function space. Okay, that will make sense in a little bit. So let's start over here. So let's say I have a PDE, and let's say I take the let me make an example. So let's say I have a cylindrical drum. So this could be the top head of a tabla, let's say, without any markings inside. It's just one single membrane. It's a membrane, and the membrane is clamped on all sides. Okay. Not only that, this membrane is elastic, so I can in principle hit it and then it will vibrate. Okay, I can hit it a little bit like this, it will vibrate. I can hit it with a different force, it will vibrate differently, and so on. Okay, so this membrane vibrates in response to a force, to let's say an impulse. Okay. Now I want to find out what are the shapes, what are the various shapes and frequencies. Of vibration, right? I can ask the question, what is the frequency with which it will vibrate? Maybe in one mode it will vibrate slower, in one mode it will vibrate faster. In which case, if let's say this was the head of a tabla of some form or a drum of some form, it has braces to make sure that the ends are all fixed. So circumference is fixed. Everywhere it's clamped down, right? If you've seen a tabla, you've seen that clamping around the circumference. And I want to know for what shapes, what frequencies come out, because that will result in the type of sound I'm going to hear. So depending on the frequency, if it's lower frequency or a higher frequency, I'll hear a different sound. So you can generate these different sounds from that membrane. That's the basis for a drum, right? So this is a simple enough question. It's been asked several times in the past. It's a very well-known question. It's been answered also. But in the process of answering this question, we'll find out something very interesting about initial value problems and boundary value problems. Okay, which will sort of dictate how we go about solving them in some sense. Good. So let's do this. Let me first write down the equation. So it doesn't matter if you don't know what the equation is. I'll give you the equation. It looks something like so. If the displacement of the drum, let's call this phi. So the vertical displacement of the drum at different points, and since this is a circle, I'm going to use a circular coordinate system, right? So this is capital R, or let's say R naught, or A. Okay, let's say A. Okay. So the displacement, so phi is the vertical displacement of the membrane. And it's obviously a function of r. So if I look from above and look at the thing, it's just going to be a circle, and any point has got r and theta, of course, polar coordinates, circular polar coordinates, and the entire drum, let's say, has a radius of small a. Okay. So phi now obeys differential equation, a PDE. It's called the wave equation. You've seen this in some form, I hope, before, but it doesn't matter. So phi obeys an equation that looks like this. Remember, phi is a function of three variables, r, theta, and t. So it has an oscillation in time, and it also has a spatial dependence. So presumably that is the distance points on the membrane that are closest to r equals small a are going to vibrate the least, presumably, because the circumference is fixed, and stuff near the middle might vibrate more, for example. Right? So it has an r dependence. It has a theta dependence also, because a priori the membrane doesn't have to vibrate in an axisymmetric manner. I could give an impulse like this, and then I let it go, and then it's going to vibrate like this, and it's not axisymmetric, right? So in general, it's a function of t, and it obeys this equation. Of course, this is the Laplacian, and in this coordinate system, it looks like this. Okay, that's what the Laplacian is. So it obeys a PDE like this. This is a wave equation. It's a hyperbolic PDE. Doesn't matter in case you haven't seen that before, but that's what it is. Now I can take this. Okay, let's assume that we're looking only for axisymmetric solutions. So phi does not depend on theta. So I'll get rid of this term. Okay, so we're looking only for axisymmetric solutions. So that gives us some hope, because now instead of depending on three variables, it depends on two. and the equation looks like this. The equation for phi, and we have to solve this. Now the boundary is kept fixed, so phi equals 0 on r equals small a, right? R is the radius. So how do we go about solving this? The usual technique. Oh, and notice this is a linear PDE, because it depends linearly on phi. There are derivatives, higher order derivatives and so on, but just like for ODEs, you don't have terms like gradient phi square and things like that, right? So it's a linear system. So for linear PDE like this, you've probably seen this technique called separation of variables, which you've probably done in an undergraduate maths course or an undergraduate heat conduction course or a wave motion course or dynamics course, something like that. But it doesn't matter if you haven't, well, or if you don't remember. The idea is very simple. You write down phi as a product of two terms, two functions, one that's a function only of t and one that's a function of r. Okay, so it depends on two variables in general. You postulate that the dependence looks like this. Now there might be a question about why you should be able to do this. It turns out you can always do this for a linear system. Okay, and the actual form is not of this, it's actually a summation, but we'll come to that. Okay, and then it will be clear why you can do this. Okay. Now if you do this, then this thing obviously simplifies, because dou square by dou t square will act only on this, and dou by dou r, whatever this is, will act only on this. Okay. So if I put this down here, if I put this down here, I'm going to get the left hand side, r will not, it will come out because there's no derivative. So it will be now d square by dt square of t, because t is a function of a single variable only, and that is c square. Now on the right hand side, t, capital T will come out because all are spatial derivatives. So you get capital T of t times 1 by r dou by dou r of r times dou by dou r of capital R. Okay. Now again, since capital R depends only on one variable, I'm going to replace this with derivative, total derivatives. Okay. So if I divide both sides by t times r, capital T times capital R, then I'm going to get 1 by t is c square by r times 1 by r d by dr of r dr by dr. Okay. And the usual argument goes that the left hand side is only a function of time and the right hand side is only a function of radius. So they both, you can't have something that's a function of time be equal to something that's a function of radius for all radii and for all t, small t. So you will set this is constant, and so the right hand side is constant. So both are constant. Okay. So you can open this up one by one. You have now two equations. Let's say the constant is some k. Just k anything, right? Yeah. Okay. K. Constant is k. So I look for first the t equation, capital T equation. So that is d square t by dt square is equal to k times t. Now remember, I'm looking for vibration solutions. So presumably I'm looking for solutions that look like sine omega t, cos omega t type of thing. And I have an equation that looks like that, but then I have this k. So if k is positive, then I'll get only exponentially decaying or exponentially growing solutions, which is not what I want, right? Second order of ODE, constant coefficients. We've seen this before. So for oscillations, we postulate that k is negative, and we set it equal to minus some lambda square. Lambda is some real number, lambda square is positive, so negative of the positive number is negative. Okay, so if you do this, then you will get t is some a. Have I used a anywhere? No, good. T is, yeah, let's do that. Yeah, t is some a sine of lambda t plus b cos of lambda t, whatever. Okay, A and B are two unknown constants, we don't know what they are, so we're going to leave them aside for now. Okay, and they have to come from the initial conditions. Okay, good. Now we've got one ODE from here. If we equate this to the right hand side, we'll get another ODE. So let's do that. So you will get 1 by r d by dr of r dr by dr is equal to k is minus lambda square because of this logic, minus, actually we bring it to the other side, plus lambda square r by c square is equal to 0. Okay. So you have one ODE, you have another ODE. What's the difference? Okay, first of all, both are linear ODEs. Okay, because we started from linear PD, we have to end up with linear ODEs. We can't have non-linearity. So, okay, till then they're fine. But this ODE had t as an independent variable, time. So presumably you're going to give conditions, the auxiliary, what we call the auxiliary conditions, at t equals 0 or t equals some initial time. So this is an initial value problem. But this guy, this fellow, you have the condition that r at small r equals a is 0, and you also have the condition that r at small r equals 0 must be bounded. Okay, that's loosely speaking another condition. This is not exactly a boundary condition in the sense that we have spoken about before, but it actually is. Okay, but we'll not go into the details. So you have two conditions. Okay. So this is the boundary value problem, this is an initial value problem. Now what is the difference between the two now? So the initial value problem we have solved, okay, we have got this for arbitrary lambda, remember lambda is arbitrary so far, it's just some arbitrary real number which enabled us to get some oscillatory solutions. We don't know the frequencies. In principle, up front, lambda is any real number. So you have a continuum of frequencies that are possible. Okay. And we don't really know anything about the frequency, we only know that solution. And notice, even if you give the initial conditions, you will still not know anything about the frequency. So even if I tell you that I have lifted it at t equals 0 by so much, and at t equals 0 I have given it this much velocity to let it go, and it's just doing its oscillation, that will still not tell me the frequency, because that will only set a and b, not lambda. Okay, so that's a property of the initial value problem. Now let's come to the second fellow, that's more interesting. So this equation, let me also take this to the other side. Okay, let me open it up. So I'll get r d square r by dr square plus dr by dt plus lambda square by c square r times r is equal to 0. So if I divide throughout by r, small r that is, I'll get this, I'll get this. Okay, yeah, that looks good. Okay. This is called the Bessel equation. Okay, and the solutions of these equations are so called Bessel functions. Okay, but now something interesting happens. The moment you have a boundary condition like this, then this boundary condition, so these solutions are Bessel functions. I won't give you the expressions of the Bessel functions. Okay, but that boundary condition, Bessel functions, you can think of them as being analogous to sine and cosine, analogous. Okay, I'll give an explicit construction now, show you an example. But they also have a frequency, they also have a wavelength. Okay, just like sines and cosines have a wavelength, sine of kr, cos of kr has a wavelength 2 pi by k. Bessel functions, you can also think of them as having, loosely speaking, some wavelength. It's not actually a wavelength because it's not oscillating like sine and cos, but okay. Okay, but now the key to notice is that the boundary condition, that second one, let me call this 1. So the boundary condition 1 picks out only certain wavelengths. Okay, and why do they have the wavelength? Because you have lambda. Okay, I'm referring to that. The wavelength presumably depends on lambda and c. Okay, so let's say wavelength depends on lambda. Let's call lambda itself the wavelength. Okay, so the boundary condition picks out only certain lambdas. We call them lambda 1, lambda 2, and so on. Whatever. In general, some lambda. Okay. And in general, there will be infinite of them. So the boundary value problem gives you discrete values of lambda which satisfy the boundary condition, and so you now have only certain values of lambda for which you will get a solution to this equation. This is the equation plus boundary condition. Okay, that means correspondingly for this lambda you have a different frequency in the time oscillating problem. Okay. Now, to see this a little bit more explicitly, maybe it's easier to do this in Cartesian coordinates. I'll show you that quickly. So, in Cartesian coordinates, we did the same thing. So, in Cartesian, so let's say now instead of a circle membrane, I have a string like this, and then I'm letting the string go like this, and I'm looking for solutions. You know, what are the frequencies at which it oscillates and so on. Okay. If I do that, then I only have an x variable and I have a t, of course, time. So now phi is a function of x comma t. The equation that we had originally, the wave equation for this was derivative of t square is c square gradient square phi. Now gradient square phi is dou square phi by dou x square. Okay. Now if I do this exact same procedure, I write phi as a function of t of t times now capital X of x. Instead of capital R of r, I am writing capital X of x. If I do the same procedure, the t equation will be unchanged. Why is that? Because the left hand side I have not done anything. I have only changed the spatial equation in going from circular polar coordinates to Cartesian coordinates. Okay. So t equation is unchanged. That will be the same. Solution will be the same. Same logic goes through to get lambda minus lambda square for k. So that is the same. But the phi equation becomes simplified, and I'm doing this just to give you an analogy with the Bessel case. Okay, so the x equation, sorry, not the phi equation. The x equation becomes like this. So you get c square by x, dou square phi by dou square capital X by dou x square equals minus lambda. So you get x is equal to square minus lambda square by c square. So t square by dx square times x. Again, this is the same equation as this. K is minus lambda square by c square now. And you do the same situation like this, and you get x is equal to some, let's call this p sine of lambda by c times x plus q cos lambda by c times x. Okay. Now, the analogy should become somewhat clearer. Okay, the Bessel function is algebraically slightly more complex, but the situation is exactly the same. Okay, that's what I want to impress upon all of you. Now, let's say in this case I have two boundary conditions. Let's say this thing is fixed, the total length, let's say, is L, and I say that the boundary conditions here are again, notice t is this, and upfront lambda is some continuous value, it does not matter what it is. Now, if I take this and then I say x at x equals 0 is the same as x equals capital N, and both are 0. So, these two ends are fixed. Okay, these two ends are fixed, and I am letting it oscillate in between. Boundary value problem, differential equation, boundary value problem. Okay, this is linear, okay, with constant coefficient, so we can actually solve the differential equation without worrying about these auxiliary initial or boundary conditions. So we have done that. Now it's a question of putting this in. Now what happens? The first condition, x equals 0, capital X is 0. That tells us that when you put x equals 0 here, this guy will be non-zero, you'll get q, so you'll get q equals 0. Okay, so you get this fellow gives you q equals 0. But this guy becomes a little bit more non-trivial. If you do this, then you will get p times sine of lambda x by c at L, so lambda L by x is equal to 0. Now obviously p is not 0, because if p is 0, then okay, the whole solution is 0, it's pointless. That means that this guy has to be 0, so only certain lambdas will work. And what are those lambdas? In this case, there's lambda L by c is 2 pi times n, so lambda is 2 pi nc by L. Okay. So that now tells you that only certain, I'll enumerate these lambdas, only lambda which is lambda 1, lambda 2, lambda 3 is 2 pi c by L, 4 pi c by L, 3 pi c by, 6 pi c by L and so on, 2 pi times nc by L. Actually this can just be n, doesn't need to be 2 pi, right, because it's sine. So any nc pi by L, so 2 pi, 3 pi, 4 pi, 5 pi, whatever, c by L will give you lambdas. Okay, so now the boundary value problem solution has picked out a certain frequency. Remember, lambda is a frequency originally, lambda by c is the wavelength, wave number, c by lambda is the wavelength, okay, because that has dimensions of length. Lambda itself has dimensions of 1 by time. Lambda by c has dimensions of 1 by time divided by length by time, which is 1 by length. 1 by length. Okay, so the boundary value problem picks out certain wavelengths. Okay, and correspondingly the initial value problem gives you the frequencies. So that's how you solve a situation like this. Okay, so in general, now clearly these two are the same, right? I mean analogous. The cylinder, the membrane, circular membrane, and this guy are the same, analogous. So it really raises the question why these solutions are considered better than, let's say, the Bessel function solutions. So this will be J0 of lambda r or y0 of lambda r. Okay, these are Bessel functions of order 0 of first kind, second kind. Now we have to ask the question, why do we usually consider these functions as being somehow more elementary than these functions? Okay, and the reason really is twofold, maybe even threefold. The first is we're very familiar with these functions compared to these functions, because right from school, whatever, 9th, 10th, 11th, 12th, whatever, you're used to manipulating these functions and not really used to manipulating these functions. But that really can't be a criterion, that's not an objective criterion for why these should be more fundamental than those, or they should be more elementary than those. The second second reason that you probably think of is that you know a series solution for this and this. So if I give you sine of x, you can expand it about x equals 0. And how will you do that? Well, you will just take sine x is equal to x minus x cubed by 3 factorial plus x power 5 by, we know that series. Similarly for cos, we know 1 minus x squared by x, whatever. So those are series about x equals 0. So we know how to solve them. So since I know the series expansion for this, it's somehow a more elementary function. Okay. Now you can get that series expansion by using Taylor series about x equals 0 again. So you can just take derivatives and put x equals 0 and then do an expansion. That's the Taylor series. So we know the series solution. Okay, that's maybe the second reason. The third reason is we know that these obey some orthogonality relations. Okay, so if I gave you an arbitrary function, let's say if I gave you, I can get rid of this, right? Yeah, let me get rid of this. So if I give you an arbitrary function like this, some f of x, then you can find an expansion like this, n equals 0 to infinity, it's Fourier series, and you know how to, or plus, okay, plus bn cos of nx, the entire sum. You can do Fourier series expansion like this. You've probably seen this before. Any arbitrary continuous function, you can do this. If you do this, then you can use orthogonality between sine and cosine, basically integral sine nx cos mx dx, either is 0 or 1 depending on whether n and m are equal or n and m are not equal. If they are equal, then it's 1. If it's not equal, it's 0. Okay, with some constant. So it's usually some constant, doesn't matter depending on the domain of integration. But you can use an orthogonality relation. This is an orthogonality relation. It means that sine of nx and cos of mx are perpendicular to each other in the sense that perpendicularity is measured by the value of the integral. So this makes this type of expansion useful. Right? This type of series is useful because what you can do now is you can just multiply left hand side by cos mx and integrate. So you will get integral f of x cos mx, and the right hand side it will only pick out cos mx from this, so it will pick out bm. That's how you do Fourier series expansion, right? So this is useful from that point of view to do Fourier series. So that's the third reason. Of course, you probably are familiar with reasons 1 and 2 that I gave you. You may be not familiar with 3, but 3 is very commonly used. Fourier series, you probably have seen them before. Doesn't matter if you haven't, but yeah, I'm just saying. So maybe that's the reason why sine and cosine are considered somehow to be more elementary than J0 and Y0. But if you think about it, all three reasons are really not unique. Okay, the first reason of course is very bizarre, it's very subjective. Experience with this does not make this an elementary function. The second reason that you can get a series expansion is also not unique. You can get a series expansion for these two too, and that's what we will do. Okay, Bessel functions you can write as a sum of series just like you did for this, which means you can get expansions for Bessel functions, derivative, second derivative, third derivative, fourth derivative, Taylor series. Yeah, you can get that for this as well. So second reason is not valid. The third reason that you can do this somehow and use this orthogonality type property to expand any function in this form, that is also not valid because there is an analogous orthogonality relation for the Bessel functions. Okay, so you can actually expand any arbitrary function in a Bessel series, just like you could do in a Fourier or sine cosine series. So really these functions are no more elementary than these functions. Okay, that's a very important thing to keep in mind. So let me actually write it down because it's important. So sine and cos are as elementary as J0 and Y0. Okay. Now you start thinking, okay, so what is it that makes these functions elementary? Why is it that you have these functions and why are they useful, right? I mean, for the sine cosine they're useful because we can do this. We can take any signal, break it up, and then look at so-called spectrum of that function, right? This n and m have some numbers depending on the domains. Have just been a little varied. There's usually a coefficient here, pi by L, pi by R, whatever, depending on size of the domain, the periodicity of f, or the size in which f is defined. Okay, but still it can be done. Right, you can expand it like this, and I've told you now that you can expand any function like that similarly in Bessel function series also. Okay, for various values of the lambda or n. Okay, and the reason why you would call these elementary are because they are all solutions of a boundary value problem. And not only a boundary value problem which picks out certain values for the wavelength. Any boundary value problem linear will do that. We've just shown that example here. So the result of this is the fact that these guys are all picking up specific wavelengths. And the consequence of this is that they also have an orthogonality. Okay, you can show from the governing ODE boundary value problem that they have an orthogonal relationship. In general, the orthogonal relationship is going to look of this form. So if I have in general any two arbitrary phi 1 of x and phi 2 of x, or t, doesn't matter, then if I have, let's say, phi I and phi j, Okay. In general, any boundary value problem, linear, non constant coefficient boundary value problem, you can write down something that looks like this. This is an orthogonality relation. Okay. And why is this useful again? This is useful because you can write any f of x. Remember, f of x doesn't have to be a solution of any differential equation at all. Okay, so you can take any a priori, of course, a priori. You can take any f and expand it in these functions. Okay, this is the analog of this. Okay, so you can take it and expand it like this. So this is the orthogonality relationship. I'm just sketching out the idea that underlies all of this stuff, so that when you see it at some point in the future, you are not completely thunderstruck. You can relate to something that we've covered already. Okay, so if given a general differential equation, second order linear, p of t or p of x, doesn't matter. I've used x here because it's sort of like a spatial variable, but doesn't matter. Okay, let's say p of x y prime plus q of x. I've just used it to be consistent with that notation that we had there. Okay, so this is of course d square y by dx square. Y is a function of x. If I have this depending on some combination of p and q, which I won't go into, you can get a corresponding r, under which solutions of this problem, this being a boundary value problem, so y of a is 0, let's say y of b is 0. For this boundary value problem, you can show that an orthogonality relation like this will hold for solutions y equals some phi k of x, whatever k equals 1, 2, 3, 4, 5, 6, right? It goes like this. Again, that's a generalized version of that. Okay, the act of determining these functions and the corresponding wavelengths or corresponding values of lambda that you see in the boundary value problem, the act of doing that is something called the Sturm-Liuoville problem or Sturm-Liuoville theory. Again, there are books written on Sturm-Liuoville theory, so there are courses that you can take on Sturm-Liuoville theory itself, talking about existence and talking about determining the solution, determining the eigenvalues, the spectrum, and so on. But they're basically going to fit in here. Okay, good. Okay, now an expansion like this is useful because you can then take, like I said, just like there, you take integral f of x phi m of x dx, integral f of x phi m of x r of x dx, like this. On the right hand side, maybe I can just write it down. So on the right hand side, you will get, from orthogonality, you will get out the constants. Okay, so if you have this, then I can write integral r of x f of x phi n of x dx from, let's say, a to b. On the right hand side, I'll have a summation, ak is constant, so that will be outside the integral. Integral r of x n integral r of x phi n of x phi k of x, oh, this is k. Okay, dx a to b, and this guy is 0 if n is not equal to k, it's equal to 1 when n is equal to k, so this will pick out only a n. Okay, so you can get the coefficients a n's by doing this. Okay, I just mentioned it since you've already done linear algebra. The procedure that we just described here, this is called a series expansion. In the phi case, okay, it's called a series expansion. And since you've done some linear algebra, this orthogonality really has the same connotation as what you saw in vector spaces, in finite dimensional vector spaces. The dimension is infinite, and you don't have to get offended by that. The ideas that you've learned for finite dimensional vector spaces apply just as well to infinite dimensional vector spaces. Okay, so what is the idea? Well, the idea is you can think of each of them as a vector, and you can think of a function as some arbitrary vector in the space of vectors, function space, what we call the function space. And any vector is a linear combination of the other vector. So this is an orthonormal basis, and normality, orthogonality being defined by this, right? So it's an orthogonal basis. We can normalize it, of course, by just dividing by the magnitude, doesn't matter. So you can get an orthonormal basis. If you have an orthonormal basis, you can just take a projection of that vector in each basis to get the value of the expansion coefficient. And that's exactly what we've done here. Okay, so there's an analogy between the linear algebra that you learned at the start and this type of function expansion. So these things are called function spaces, and the function space that you're actually interested in depends on this R, which is sometimes called a weight function, that determines the orthogonality relationship. And R changes from set of function to set of function depending on what you take. So for example, if you take the sines and cos, R of x is 1, because integral sin nx cos mx is equal to delta mn. If you take this and this, you'll get a different R. If you take polynomials, Regehr polynomials, Legendre polynomials, you'll get different R's. So you can generate a whole host of these functions, okay, and you can write down an expansion, series expansion like this in the corresponding set of functions. Okay, so the why do we want to do this? Well, firstly, you can do this. Of course, you can get the coefficients. Each of these functions is linearly independent. Sine and cos are linearly independent, right? But there is a small difference from all our considerations of initial value problems to now. The difference is that the functions, there are infinite of these functions now. There you had only one sine, one cos, but the frequency was fixed up front in the initial value problem. In the boundary value problem, you have the frequency falling in a range, an infinite set, but all distinct, discrete values. And so you have discrete frequencies, correspondingly you have discrete functions. And so now you have to take that entire set and you have to create a completely infinite set of these functions, as opposed to just 2 by 1 by 2, you have phi 1, phi 2, phi 3, phi 4, etc. Like you have sine of n is equal to 1, n is equal to 2, and so on, right? Like this. So that's why the boundary value problem becomes more complex. And you can trace this entire complexity back all the way to the thing in phase space that I spoke about. So there your trajectory was starting for the initial value problem at a given point, and then you knew where it could go. You could trace it out in principle, but now trajectory starts anywhere on this line, ends anywhere on this line, and so, and it ends at a specific time, let's say t, some t. Then you have a whole host of possibilities which you have to now evaluate in some sense. Okay, so that's sort of the analogy that you have between that case and this case. Okay. Now this also has physical significance, which is that if you open it up like this, let's say, if I did the analog with the Bessel functions, J0 of some lambda times R, let's say lambda by C times R, if I opened something analogous to this with the Bessel functions, then the coefficients will tell me the magnitude to which that particular mode is activated. So if I go back to the drum problem, this was my circular membrane fixed along the circumference. If I give it some initial pinch and let it go, if it's axisymmetric, so I give it along the origin, then this will tell me, the coefficients in that corresponding expansion and Bessel functions will tell me how much of the amplitude corresponds to a certain mode with a certain lambda. Okay, just like if you had the string, you did the same thing. What you're actually taking and doing in some arbitrary oscillatory form like this, depending on where you let it go and so on. If I let it go like this and it just goes back and forth like this, it oscillates. So it tells you how much of the actual amplitude, how much of it is in each of those wavelength modes. So first wavelength mode could be, let's say, like this. Second could be like this. Let's say third could be like this, and so on. So by doing this type of expansion, you're actually seeing how much of the actual value is in each of these modes. Okay, and for the vibration problem at least it's useful, because then it can tell you which is the primary sound that you will hear, because the oscillation is going up and down. This is the wavelength, the oscillation is going up and down, and so in this problem the string is, if it's done in a suitable frequency range. This thing is going to go oscillate like this, and so that's going to set off pressure waves that are going around in the atmosphere around, and those pressure waves eventually come to your ear and you pick up a pitch. Okay, so that's why this boundary value problem, fixing the frequency, fixing the wavelengths and consequently fixing the frequencies in the t, where we had k equals minus lambda square, the t, capital T of t in that function, that becomes important because that is finally what you're going to hear. Okay, so if you change, for instance, the length of the string, then you will get a different value of L. If I change the length, I'll get a different value of L. And this, because the boundary value problem sets the frequencies that you can pick, this will give you different set of frequencies, not the same as the previous problem, it will give you a different set of frequencies, and that will give you a different set of lambdas for the oscillation, the T, capital T problem, and that will give you a different pitch that you will hear at the end. So the sound frequency will change. That's how a violin is played, right? You play it at different points, you get different frequencies, or you change the length and you play it, you'll get different frequencies, or a guitar, whatever. Okay, and so that's the basic idea for where this comes from. So really the distinction between an initial value problem and a boundary value problem should be clear first. Second, the fact that you can expand any function in this series should also be clear. So we can take a solution, let's say f is actually the actual solution of the problem, okay, and it's expressed like this, then I can take any actual solution and break it up into these what are called modes. Right, each of these is 5Ks with a corresponding amplitude, and I can solve the original problem now. Okay, so that's another important thing that you want to keep in mind. So you will see this often when you talk about PDEs, and usually separation of variables technique is, at least algebraically, it's very straightforward to work out. You do whatever, but finally when you come to the actual content, there is a lot of physical subtlety that is involved in this process. Okay, good. So what we'll do now is I will talk a little bit about, now series expansions are very useful, right, because they're giving you this sort of break up into various modes and frequencies and things. So what we'll do now is I'll talk a little bit about series solutions and how to get them. Especially we won't look at arbitrary. Now this is arbitrary phi, right? Phi defined by this orthogonality being a solution of some ODE for which a suitable R of x can be found. But instead of doing this, we'll do a more simple case. So our functions will not be orthogonal, but they will just be polynomials. Okay. There is a way to get orthogonal polynomials out of this with a suitable R depending on a differential equation that you start from. But in the interest of time, we'll just do the simple what are called power series expansions or power series solutions. Okay. Now remember, again let's recall f of x is sigma a n phi n of x, n equals 0 to infinity. You have infinite terms, you're adding them all up. Phi 0, phi 1, phi 2, phi 3 are all solutions of some ODE. F is also presumably solution of that same ODE, but we want to find what it is by splitting it up into this. Now there is a more generic version of this which we can do for any ODE, okay, not necessarily for this. This is a general series expansion. But purely by analogy, if you have a differential equation dy okay, this is my differential equation, second order non-constant coefficient. If it's constant coefficient, it's very trivial to solve, but non-constant coefficient, this depends on t. Okay, this is my differential equation. Then I want to ask the question, what are the solutions? Okay. Okay, why we picked this? Okay, let me say a couple of things about that. So let's say I have an arbitrary second order equation. This obviously doesn't have the first derivative. I think maybe I mentioned this before, but if I didn't, I'll do it again. Okay, so let's say this is my arbitrary second order differential equation with non-constant coefficients. it's non-homogeneous for now, because remember, if I know how to solve the homogeneous problem, I can solve the non-homogeneous problem by variation of parameters. We've seen that, right? So I'll work with this. If I define y is equal to w, let me say u of t times w of t, that y prime is u prime w plus w prime u, y double prime is u double prime w plus w double prime u plus 2u prime w prime. If I put this back in, I'm going to get y double prime is d square by dt square. Okay, that's kind of understood. So I'm going to get u double prime w plus w double prime u plus 2u prime w prime plus p times u prime w plus u w prime plus q times uw is equal to 0. So now I'm going to collect all powers of w double prime. This only has a u. W prime has 2u prime plus pu plus w has u double prime plus pu prime plus qu. Okay, I've just taken y, I've made some arbitrary substitution, okay, as a product of two functions, whatever they are, I don't know what they are right now. And why am I doing all this stuff? Well, I'm trying to show you that you can take any general second order ODE of this form and reduce it to this form. So if I ask you how to solve this equation and if I give you a solution for this equation, then presumably by reforming from here to here, I can get a solution of this equation. Okay, it's fairly standard. So how do I bring this to this? Well, now I just set the coefficients of this term, w prime term, to 0. So then I'll get 2u prime plus pu is equal to 0. So I can solve for u. Here there will be one unknown constant, that is fine. So I can solve for u. I can solve. And w, so then I can put this back here and then I will have w double prime plus 1 by u times u double prime plus pu prime plus qu times w is equal to 0. Okay, and I'll call this entire thing, and since u of t is known, this entire thing is a function of t, I'll call it capital Q of t. Okay, so w will now satisfy this equation. So y satisfying this is analogous to w satisfying this with a known q, or with a known u, sorry, and that depends on p. Okay, so I can take any equation of this form, any general equation, reduce it to this form. Okay, so this should convince you that studying this problem is useful because I can map back. Okay, so a standard way to find the solutions is by using what is called a power series expansion. Okay. Okay, so what we do there is we use y is some an, and this power series expansion is usually about some point. It has to be about some point. We'll just take about t equals 0. Okay, so that gives me an expansion like this is a power series expansion about t equals 0. In general, if I had some about t equals some arbitrary t naught, it will be like this. Okay, this is about t equals t naught, power series expansion. Now this power series expansion is interesting. First, when do you guarantee that you can write an expansion like this? Which means that if I have a series like this, I have infinite terms. How do I know that if I sum that series on the right hand side, the sum is going to be equal to y? Okay, when will it be equal to y? And for that we need to check for what is called convergence. Convergence of a series. It's a very simple idea. You just take the limit as n goes to infinity of the coefficients an divided by an plus 1. Take the magnitude. If that's less than infinity, if that's less than 1, then this guy is bounded. Okay, if it's bounded, then it's going to converge. Okay, which means that progressively the terms, sorry, it should be an plus 1 by an. Progressively terms are becoming smaller and smaller. Okay, so that's what this means. But this series also has an important consequence. If you try to recall any other series that looks somewhat like this, the one that you will remember is probably a Taylor series. Okay, if you remember Taylor series expansion, you've probably done this at some point. And any arbitrary expansion of this can be shown to coincide with the Taylor series if the function is well behaved. Okay, it doesn't have any singularities. How do you do that? Well, you take y, again, let me expand about t naught equals 0, it makes life easier for all of us. Take an expansion like this, take a derivative, so you take dy by dt. First you take y of 0 is a0, because all the other terms have t power n, and n is 1, 2, 3, 4, they are all 0. Okay, so this expansion is about t equals 0. Okay, if I had some other t naught, I'll have t minus t naught like this, and then I'll have to evaluate y at t naught. That will give me a naught, because all the other terms will go to 0. Okay, just keep it in mind. If I take the first derivative, okay, then I'm going to get n t power n minus 1. Now n goes from 1 to infinity, because n equals 0 is gone when you take the derivative, right? And if I calculate this dy by dt at t equals 0, I will get on the right hand side terms from n equals 2 onwards will go off to 0, because they will have t to the power of 1, t to the power of 2, and so on. But the first term n equals 1 will not be 0. That will give me n times a1. So n is 1 again, so that will give me a1. I can calculate third term, of course. Again, I can do the same thing and keep going. Now n goes from 2 to infinity. I'll have n times n minus 1 times an t power n minus 2. And if I do this at y equals 0, I'll get d square y by dt square. A2 times 2 into 1, that's 2 factorial. And I can keep doing this forever. So in general, the nth term will be dn by dt n of y at t equals 0 is equal to n factorial times an. Okay, so the nth term I can get out easily like this. It will just be 1 by n factorial times this. So this is actually a Taylor series expansion for y. What is the problem? To calculate all the coefficients, you need all the derivatives. We don't know the derivatives because we don't know the function. That's what we're trying to find out, right? So even though this is a Taylor series expansion, this is the inverse problem of the usual situation. Where usual situation you do Taylor series expansion by taking the function, expanding it out, taking its derivatives and so on. But here we're calculating, we have to rather calculate the derivatives a0, a1, a2, the coefficients a0, a1, a2 and so on, and then put that back and then get the function to a reasonable amount of approximation. Okay, so this is the inverse problem of the usual Taylor series. So y equals sigma n a n t n. So inverse of usual Taylor series. Okay, and that's good because we are now in a position to appreciate two things. First is that depending on how many ANs we calculate, we've presumably got a better approximation for y. So the more ANs, the better the approximation. Okay. Because you have got more derivatives of y to actually calculate. Okay, I'll give you a geometric picture of this. If you have let's say this is t and this is y, what you actually want to find out is you're given the initial condition. Okay, this is y of t equals 0, this point, let's call it y naught. You're given the initial condition, the actual function looks like this. The function that solves the differential equation looks like this. And you want to find out the value of the function at some arbitrary t. Okay, let me draw it like this. You are given the value at t equals 0 and you want to find the value at some arbitrary t that is away from t equals 0. That's what you are doing, right? If I calculated only the first term, so I will have y equals sigma n Tn, n equals 0 to infinity. If I calculate only the first term, then I'll say y is equal to a naught. So this is, let's say, a naught. Then y, this is y of t, remember, so y of t. If I use, so this is plus a1t plus a2t square plus blah blah blah, whatever, infinity. If I calculate only the first term, then I have only a naught. That means my approximation to the function is like this. So I'm actually approximating this function by this horizontal line, which is quite bad, right? So if I now go and say, okay, let me take another second term, and let's say I calculate a1. Now remember, I haven't told you how to calculate a1, but assume you can, and I'll show you how to do that at the end. If you can calculate a1, that means you have got a1, remember, was dy by dt at t equals 0. So if you can calculate a1, that means you've got the slope. You have the value already that's given to you, that's part of the initial condition, let's say. But now you also have the slope. If you have the slope, then what I am doing, if I just truncate here, what I am doing is I am taking the value plus slope times t. T is t minus 0, of course. So I am basically taking the slope of this curve here, and then I am doing a linear approximation. So this is a1 times t, this is a0 at this t, of course, this value of t, whatever that is. Now it's still kind of, there is a discrepancy, okay, you know, you're like, okay, I want a better value, so add another term, t square. What do I do now? Now I'm assuming that this function is local like a parabola, okay, a0 plus a1t plus a2t square, parabola is a function of t, so presumably I'm going to get, I'll take the second derivative, and presumably I'm going to get something that's a little bit closer. So this distance is a2t square, and so on. So eventually, if I put more and more and more terms, I'll get closer and closer and closer to the actual solution. Okay. And now, how many terms do I need to actually converge? That's another question you can ask. Right? How many do I need? How many terms in the series should I actually be calculating before I can say that my actual solution is good enough? Well, in principle, you have to calculate all infinite of them, because there are infinite of them on the right hand side. But in practice, you can get away with a few of them. Okay. There is a very interesting analogy between these two questions. One is, does it converge? You already answered that. And the second is, how quickly? Okay, I'll give you two analogies, two analogous questions that we have seen, probably one at least you have seen in this class, another one you've probably seen before. The question of does it converge is, yeah, okay, you can solve that question. You just take limit n goes to infinity. Presumably, if you have calculated all the n's, so you take a n plus 1 by a n, and then you see if this ratio magnitude is less than 1, and then it's going to converge, right? You've answered that question. For the particular expansion that you have in mind, remember, an's are not known, you calculate them in some way. I'll show you that way again, repeating myself, but once you calculate them, you can calculate the derivatives of y. That's the whole sort of inverse idea that we've spoken about. And you can do this ratio thing, and then you can get whether it will converge or not. You can get the range in which it will converge, things like that. But how quickly is a very different problem. For this, you have to do compute. You take term by term by term, and then you see how quickly it's going. There are some results, some tests that you can use, but we won't go into that. But the standard route that you can, the foolproof route, is to just compute. You take 2 terms, you see how close you are, take 3 terms, 4 terms, 5 terms, 6 terms, keep seeing how close you are. And if you see the distance, the magnitude of y of t minus n equals 0 to let's say some capital N, this magnitude will start reducing as capital N becomes larger and larger, usually. Okay, that's the sign that you're coming closer and closer to the actual solution. Okay. So there is the direct analogy between these 2 questions is what we were doing when we did qualitative analysis, right? In that case, the stability of a fixed point was sort of analogous to the first question, and the actual solution that you solve, that you work out, is analogous to the second question. Because the first question will tell you, okay, is it going to reach a fixed point, or is it going to go away from a fixed point, because is this fixed point stable or unstable, or so on. And the second one will tell you how quickly you will reach the fixed point, right? Because that will give you the entire, if you solve the solution y of t, then it will tell you how quickly you will get to the fixed point. Okay. The other analogy you can think of is this is like a question in thermodynamics, what is the stable state of a system, and this is like a question in kinetics. It tells you how fast the system goes to the stable state, right? So, they are 2 very complementary questions, but independent of each other, largely. Okay. Good. So, now we know that if you take more and more terms, you will get closer and closer to the solution. Good. Now, how do you get these terms? That is the big question. Okay. How do you get these terms after all? And the answer is actually surprisingly simple, although it can be algebraically complicated. It's conceptually very, very simple. You take this expression. Remember, you are expanding about t equals 0. Please always keep that in mind. Take this and put in ODE and then compare term by term. Okay, and then you set the equation, the coefficients of each term is 0, and you get a1, a0, a1, whatever, for any n. And depending on how many of these coefficients equal 0 equations you are willing to solve, you can get more terms in the expansion. Okay. Usually these are given in the form of what's called a recurrence relation. I will give you an example where you can see this happens. Recurrence relation, okay, which means it tells you a2 or a3 is a function of, you know, something 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 times a0, something 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 times a1 and things like that. But this is basically what you do. Okay, the key is in this term, doing this term by term thing, and you can do that because the functions that are there in the expansion, remember this we said is a general series expansion, which is power series expansion. For a general series expansion, the phi 1s, phi 2s were all orthogonal previously when we were talking about that. But here t1, t square, t cube and so on are all independent. They are linearly independent functions. And what do we mean by linearly independent functions? Well, we have this Wronskian, okay, Wronskian of t square and the Wronskian of t square, t cube, whatever. You can calculate all of these and you will see that these are linearly independent. Okay, determinant is 0, Wronskian is 0. Okay, so because they are all linearly independent, if you have a sum of linearly independent functions with some coefficients, then each of those coefficients has to be equal to 0, and that's exactly what you do here in this step, and then you get the final answer. I'll work out an example now, and then you can see how this works, and then I'll give you one exercise as part of the next assignment that you can work out. Obviously, I'm going to do the less complicated one here because I have a smaller board, and presumably you have a bigger piece of paper or whatever, but it's instructive to go through this process because it's a very general procedure. It always works. Let's do example, trivial example, but insightful nonetheless. Is this okay? We know how to solve this. Of course, we can just sine and cos, right? Whatever, sine t, cos t. But we'll solve this using the series solution because it will give us some important information. if I put y is equal to sigma an t power n equals 0 to infinity, I put this back in here. Okay, so then the first term will take a derivative here, an times n minus 1 t power n minus 2, and the second term is just this, and this goes not from 0 but goes from 2 because a1 t1 derivative is not there, a0 t0 derivative is not, second derivative is not there. Okay, so it starts from n equals 2. So now if I put this sum together, I'll get n equals n minus 2 to infinity n into n minus 1 times an times t power n minus 2 plus a second sum which goes from 0 to infinity an t power n, and the whole thing should be equal to 0. And so I can simplify this easy enough. This I'll replace n minus 2 to be n to be m, sorry, in which case I will get sigma m equals 0 to infinity, n will become m minus m plus 2, so it will be m plus 2 into m plus 1 times a m, n is m plus 2 times t power m, n minus 2 is m, plus sigma n equals 0 to infinity a n t power n is 0. The two sums, one indexed by m, one indexed by n, both going from 0 to infinity, so I can just replace everything by a common index k or m or n or whatever. So then that will give me, if I replace that, it will give me a single sum. Let's say k equals 0 to infinity, k plus 2 times k plus 1 times ak plus 2 plus ak, the whole thing multiplied by t power k is equal to 0. So I have a thing that looks like some constant times 1, some constant plus some constant, some other constant times t plus some other constant times t square plus blah 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 equal to 0. So each of the constants, because they are all linearly independent, each of those constants has to be 0 by itself. So if I do that, I'm going to get ak is equal to minus k plus 2 into k plus 1 times ak plus 2. Or alternatively, I have ak plus 2 equals minus ak divided by k plus 2 into k plus 1. So this is a recursion relation, a recurrence or a recursion relation. Okay, you can write the higher k's in terms of the lower case. Okay, good. So now we can start enumerating this, right? Depending on how far we want to go, we can start enumerating this. So for example, a0 we don't know what it is, because a0 is written in terms of a2 and a4 is written in terms of a2, a6 in terms of a4 and so on. So, and notice there is no ak plus 1 here. Okay, so it's only ak plus 2 and ak. So the whole series splits into two, one with the odd terms, one with the even terms. The odd term starts from k equals 0, even term starts from k equals 1. Okay, so you can do that easily. So you'll get a2 is minus a0 by k is 0, so it's 2 into 1, that's 2. a4 is similarly minus a2 by k is 2, so it will be 4 into 3 and so on. So this is a0 by 4 factorial and so on. So I'll get a6, a8 and so on. All the even guys will come here. The odd fellows will come here. a3 is minus a1 by 1 plus 1, 3 times 2. a5 is minus a3 by 3 plus 2 is 5, so it will be 5 into 4, that is a1 by 5 factorial and so on. Okay, and if you look closely, these are the two functions we had, the two linearly independent solutions. The whole thing is split into two families. This is the linearly independent, this is cosine, this is sine. The expansion, you know the Taylor series expansions for sine and cos, and this is what they are. So you've recovered the Taylor series expansions for these functions just by doing this technique without knowing anything about sine and cos. Okay, so if I didn't know the solution to this equation, if I went through this entire process, what I'll discover is that there is a series solution about t equals 0, and that series solution basically reproduces the Taylor series expansion. I can do the exact same thing for the Bessel equation. Remember the Bessel equation? It's a little complicated because there will be one t term on the right hand side. It's a non-constant coefficient case. It's homogeneous still, non-constant coefficient. Remember the Bessel equation, right? We had this, so we had d by dt. We had 1 by r, right? R is independent variable was small r, now I'm making it small t, doesn't matter. So in this notation, it's going to look like this, plus some constant times r, yeah, is equal to 0. This is what we had, Bessel equation, something like this, right? You can do the same procedure, exact same procedure, start, write y is equal to a n t n, put this in, put it into the ODE, compare term by term, split it up, coefficient equal to 0, and you will get a recurrence relation over there. You will get the analogous expansion for Bessel function, you will get the analogous derivatives of the Bessel function, and you will get an expression for the Bessel function. So in this sense, this is what I was talking about earlier. The fact that you know all this for a sine and cos is what makes it elementary, and you know all this for Bessel now. Presumably, if you do this exercise with Bessel functions, you will know all this for J0 and Y0. And so Bessel and the two Bessel functions can also be thought of as elementary functions. Okay, so that's just something to keep in mind. Good. So I can use this, maybe I should just summarize. So I can just use this for any type of ODE, linear, non-constant coefficient ODE. I can do this and I can get a solution to any degree of accuracy depending on how far I am willing to go with the terms. Okay. So if I go back to the big picture, I had the PDE, I had separation of variables, and inevitably if I worked in some cylindrical coordinates, so I had an IVP, usually IVP plus BVP, but doesn't matter. If I work in coordinates, let's say cylindrical coordinates, okay, then I will be left with a ODE with non-constant coefficients. Okay, and to this I assume y is equal to sigma a n t power n to infinity, and then after this I do star, let's say I do star, and this entire procedure is star. So I get multiple, let's say the separation of variables, I get multiple ODEs with non-constant coefficients, and then I do the star process. So I will get a solution to some reasonable amount of accuracy which I am happy with. So I will get solutions to all the ODEs using the same procedure, star for each of them. Remember, this gives you multiple ODEs, and then I will combine all with the boundary conditions. This will give me a selected set of wavelengths if it's a boundary value problem, and this will give me the final expression. Okay. So this entire procedure will summarize whatever you've seen from the start to the finish. So you start from the PD, you go all this, through this entire process, and then you come here, you combine all this with boundary conditions, selected certain wavelengths, certain lambdas that you find there, and then you put everything together, you get the final expression for the original PDE problem. So you've got a solution to the original PDE problem. Okay, this PDE is linear, of course, it's linear, but it can have dependence on the spatial coordinate, on the time coordinate, and so on. In general, for any linear PDE, you can get a solution like this. Now, in this entire scheme of events, if you have seen the separation of variable thing before, you have probably come from here, you have gone here, but you have bypassed this most likely, and you have gone here, and then you have gone here and done this. Okay, this is what you have done in a standard undergraduate level PDE course, separation of variables. This is probably what you have done. Now what we have done is we have come from here with this, especially with the series technique, is we have come here, we have done this, and we have done this. Okay, because we know how to do this, right? I mean, this is standard solution, right? So we have come till here. So now you can, in principle, if I gave you a PDE, complicated PDE, which you have not seen in an undergraduate class, you should be, in principle, able to go through this exercise from what you know from before, go through this exercise from what you know now, and then recontinue the original exercise from what you know before and get the final solution. Okay? So I hope this entire sequence of events is clear, because this is the basis for standard solutions of or series solutions of partial differential equations. We have studied it only in the context of ODEs, but this is how the entire picture will actually look like. Okay. Now there are some, of course, subtleties in this entire scheme. For example, the question, when does the series converge? You can ask the converse of that, when does the series not converge, or when is there no series expansion like this? And there are certain points about which you cannot get a series expansion. There are points at which some coefficients in the ODE become singular, become infinity, and these are called singular points. So you can expand, you can get one solution about a singular point, but you can't get the other solution. Remember, this sine and cosine, the split happened, that need not happen, right? And so there are more intricacies, so you have to be able to somehow tweak a form of the solution, and you change the form of the series. Instead of doing this, you do something else. It's called a Frobenius series. It doesn't matter for now. Unfortunately, we don't have time to go over it. But once you do that, then you can tweak it and get a solution near what is called a regular singular point, and then you can expand about certain points. You can do asymptotics, what are called asymptotic expansions, and this, the whole area that is associated with this. This is a starting point for almost all of them. So what I would expect is that you understand this procedure. First of all, you understand the motivation for this procedure, and you understand how to close the loop. Okay, to go from here to here, this is the final part that you need to get to. You should know how this loop works, and you should be able to appreciate the various parts in this loop. Okay, if you can do that, then I think we have come a long way from where we started. Okay, so what I'm going to do next in the final session, I don't want to overload you with a lot of information for this, especially for the final session. I will briefly describe some ideas that go into considerations of a numerical scheme. Okay, now if I give you an ODE, the most naive thing you can do is just do finite difference, replace dy by dt by yi plus 1 minus yi divided by delta x or delta t, whatever, and you can just write that as an algebraic equation and solve. Okay, that's possible. But there is a systematic way to do it. There are different types of differences, central, forward, backward, that you can do. There are different types of quadrature rules that you can use. So I'll give you a brief idea of some of them and what the errors are, what they entail, and so on, so that you have some idea of where this thing can go. And then once eventually you, maybe if you're interested, you can pick this up from a certain point and then follow a program of probably self-study or something like that. Okay, so this should give you an idea of the steps involved basically in any numerical scheme for ODEs. Okay, similar types of ideas will apply to PDEs, and if you follow this type of scheme, then you have some flavor of what you can do with PDEs apart from the trivial PDEs that you probably encountered before. Okay, so we'll stop with this, and then we'll conclude in the next session by discussing numerical schemes.